Welcome. It's lovely to have you here tonight. Before we begin this gentle journey through one of the most mysterious and beautiful areas of science, I'd love to know where in the world you're resting. Perhaps you're tucked beneath warm blankets in a quiet bedroom, or maybe you're on a late-night train watching city lights blur past your window. Wherever you are, I hope you're comfortable, safe, and ready to let your mind wander through ideas that shimmer at the edges of understanding. If you enjoy these soft explorations into science, a like and subscribe really helps this channel continue. And to those of you already here, already listening, thank you. Your presence means more than you know. Tonight, we're going to explore quantum physics, the science of the very small, the impossibly strange, and the quietly profound. I'll try not to make it so interesting that it keeps you awake, but if it does, at least you'll understand why reality isn't quite what it seems. So settle in, close your eyes if you'd like. Let the day drain away. And let's begin our journey into a world where particles dance between existence and possibility, where observation changes reality, and where the universe whispers secrets in a language we're only beginning to understand. At the turn of the 20th century, physics felt almost complete. The great minds of the previous generations had mapped out the laws of motion, cataloged the behavior of heat and energy, and woven light itself into the elegant framework of electromagnetic theory. Newton's mechanics described how objects moved with clockwork precision. Maxwell's equations unified electricity and magnetism into waves that rippled through space at the speed of light. Thermodynamics explained why steam engines worked and why time moved in only one direction. It was a golden age of certainty, a time when physicists could look at their equations and feel satisfied that the universe had been understood. Some even believed that all the fundamental questions had been answered, that only minor details remained to be tidied up like dust in the corners of an otherwise immaculate room. Lord Kelvin, one of the great physicists of the era, famously suggested that there were only two small clouds on the horizon of physics. Two tiny mysteries that didn't quite fit. Everything else, he implied, was settled. How wrong that assessment turned out to be. Those two small clouds would grow into storms that reshaped everything we thought we knew about reality. One of those puzzling corners involved something remarkably simple. What happens when you heat an object? When you warm a piece of metal or hold a glowing ember, it radiates light. First, it glows dull red, then orange, then yellow, and finally, if you can heat it hot enough, it shines white. This phenomenon, called black body radiation, was easy to observe. It happened every time you looked at a campfire or a forge. And yet, when physicists tried to calculate how much light should be emitted at different temperatures and wavelengths, the mathematics refused to cooperate. Classical physics, using the well-established equations of the time, predicted something utterly absurd. According to the formulas, as you increase the temperature of a black body, it should emit more and more energy at shorter and shorter wavelengths, particularly in the ultraviolet range. The problem was that this prediction spiraled out of control. The equation suggested that a heated object should emit infinite energy at high frequencies, a scenario so impossible and ridiculous that it was nicknamed the ultraviolet catastrophe. No amount of tweaking the classical equations could fix this. The math kept producing nonsense, and reality stubbornly refused to match the predictions. Something fundamental was missing from the picture. Enter Max Planck, a German theoretical physicist with a reputation for careful, methodical thinking. Planck was not a revolutionary by nature. He believed deeply in the classical worldview and had no desire to overturn the foundations of physics, but he was also pragmatic, and when faced with the black body radiation problem, he tried something quietly audacious. On the evening of October 7th, 1900, Planck arrived at a formula through a mix of intuition and inspired guesswork that seemed to fit the observed data. Heinrich Rubens confirmed within days that Planck's formula matched experimental results precisely. Planck presented this breakthrough at a meeting of the German Physical Society on October 19, 1900. To make the mathematics work, Planck introduced a strange idea. What if energy couldn't be emitted in just any amount? What if, instead of flowing smoothly like water, energy came in tiny, indivisible packets, like coins that you can't split in half? These packets would represent the smallest possible units of energy. He called them quanta, from the Latin word for how much. This was a dramatic departure from the continuous view of energy that classical physics had always assumed. Instead of a smooth, unbroken flow, energy would come in discrete steps, tiny jumps that depended on the frequency of the radiation. Planck even introduced a constant, now known as Planck's constant, to describe the size of these energy packets. It was an unimaginably small number, but mathematically, it was perfect. When Planck plugged this idea into his equations, something remarkable happened. The infinite energy problem vanished. The math suddenly worked. The predictions matched what was actually observed in laboratories. Planck had solved the ultraviolet catastrophe with a single, elegant assumption. And yet, he didn't quite believe it. In fact, Planck himself viewed his solution as little more than a mathematical trick, a clever way to make the numbers behave without necessarily describing how nature actually worked. He assumed that future physicists would find a better explanation, one that wouldn't require such odd assumptions about energy coming in lumps. Quantization, to his mind, was a temporary patch, not a revelation about the fundamental structure of reality. But history had other plans. What Planck couldn't have known at the time was that his seemingly modest fix would become the cornerstone of an entirely new way of thinking about the universe. His idea that energy comes in discrete packets laid the groundwork for quantum theory, a framework that would soon unravel much of what classical physics had taken for granted. Looking back, it's easy to see this moment as the beginning of a revolution. But at the time, it felt more like a curious footnote than a paradigm shift. Planck hadn't set out to challenge the foundations of physics. He just wanted his equations to work, and yet by introducing quantization, he had struck the first match in what would become a slow-burning fire, one that would eventually illuminate corners of reality that no one had ever imagined existed. This humble beginning, tucked into a quiet paper, published in 1900, didn't announce itself with fanfare. There were no grand declarations, no sweeping manifestos, just a small, constant, a new way of thinking about energy, and a curious little fix for a problem that refused to go away. From that point forward, physics would never feel quite finished again. The door to the quantum world had been opened just a crack, and soon others would push it wide. By the early 1900s, light was thought to be fairly well understood. Thanks to James Clerk Maxwell's groundbreaking equations, scientists had demonstrated that light behaved like a wave, an elegant ripple in the electromagnetic field that filled all of space. Light could be bent, reflected, refracted, and made to interfere with itself, creating beautiful patterns that could only be explained if light were indeed a wave, Everything seemed to fit neatly into place. But then came a puzzle involving metal, light, and electrons, a riddle that would shake the foundations of what physicists thought they knew. It was called the photoelectric effect, and it worked like this. Shine light on a clean metal surface, and electrons are ejected from that surface. The idea made intuitive sense. Light carries energy, so when it strikes the metal, it should transfer some of that energy to the electrons, knocking them free. But here's where things got strange. According to wave theory, if you increase the brightness of the light, you should increase the energy delivered to the electrons. A brighter light carrying more energy in its waves should shake electrons loose more effectively. That was the expectation, and it seemed entirely reasonable. Except that's not what happened. In careful experiments, scientists discovered something deeply puzzling. Making the light brighter didn't increase the energy of the ejected electrons. What mattered most was the frequency of the light, the color. If the light was below a certain frequency, even the brightest beam wouldn't eject a single electron. But if the light was above that threshold frequency, even a dim glow could knock electrons free with ease. There was a sharp cutoff, and it made no sense under the wave theory of light. This little inconsistency grew into a full-blown mystery. Classical physics couldn't explain it. The wave model of light, so successful in other areas, seemed to break down entirely when it came to this simple experiment. Enter Albert Einstein. The year was 1905, often called his miracle year, a 12-month period during which Einstein published several papers that would change physics forever. One of those papers, published in March 1905, tackled the photoelectric effect, and Einstein's solution was both bold and elegant. He proposed something radical. What if light wasn't just a wave? What if, under certain circumstances, it behaved like a particle, a tiny bundle of energy traveling in a straight line? Einstein suggested that light was made up of individual packets of energy, which he called quanta of light. These packets would later be known as photons. Each photon, Einstein said, carried a specific amount of energy determined by its frequency. The higher the frequency, the more energy each photon contained. If a photon had enough energy to overcome the binding force holding an electron to the metal, it could knock that electron free. If it didn't have enough energy, then no amount of photons, no matter how many or how bright the light, could do the job. It was like trying to open a locked door with a handful of keys. If none of the keys fit, it doesn't matter how many you have. You're not getting in. Similarly, if the photons didn't have enough energy, the electrons stayed put. Einstein's explanation built directly on Planck's earlier work, but it went further. Planck had used energy packets as a mathematical convenience, a way to make his equations behave. Einstein was proposing that light itself was actually made of these packets, not as a mathematical fiction, but as a literal description of reality. Light was quantized. This was a revolutionary claim, and not everyone liked it. Many physicists held tightly to the wave model of light. After all, light clearly exhibited wave-like behavior. It diffracted around corners, created interference patterns, and did all the things that waves do. If light was really made of particles, how could it also behave like a wave? Einstein didn't deny the wave nature of light. Instead, he proposed something even stranger. Light was both a wave and a particle. It could act like one or the other depending on how you observed it. This duality wasn't just a quirk of measurement or a limitation of our instruments. It was fundamental to the nature of light itself. Imagine sunlight streaming through a window. It spreads and ripples like a wave, bouncing off surfaces and bending through glass. But zoom in, way in, and you'd find tiny packets of energy, each with its own frequency, each colliding with atoms and changing the world one interaction at a time. Light wasn't simply a wave or simply a particle. It was something more subtle, something that refused to fit into the tidy categories that classical physics had always relied on. This idea of wave-particle duality is one of the strangest concepts in all of physics, not because it's mathematically complicated, but because it challenges the very categories we use to describe reality. In the everyday world, things are either particles or waves, not both, not neither, and certainly not whatever they feel like being depending on the situation. But the quantum world doesn't ask for permission to make sense. Einstein's photon explanation of the photoelectric effect didn't just explain the experimental results. It did so beautifully and precisely. The energy of each photon depended on its frequency, exactly as Planck had suggested, and it neatly explained why low-frequency light, no matter how intense, couldn't eject electrons. The individual photons simply didn't carry enough punch. The impact of this discovery was immense. In 1921, Einstein was awarded the Nobel Prize in Physics, which was actually presented in 1922 due to committee deliberations. The award was explicitly for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect, not for his famous theory of relativity as many assume. Within a decade, Robert Millikan had verified experimentally the equation Einstein had used to describe the photoelectric effect. That's how significant this insight was. It opened the door to understanding that light, the very thing that illuminates our world, refused to fit into any single box. It came in quanta. It danced as a wave. It collided like a particle. It shimmered between states, revealing just enough to keep physicists curious and just enough to keep them uncertain. What began as a simple experiment with light striking metal ended up shaking the foundations of physics. Because if light could behave this way, existing simultaneously as continuous and discrete, as spread out and point-like, what else might be lurking in the quiet corners of the universe, waiting to break the rules? The answer, as it turned out, was everything. Every particle, every interaction, every piece of matter in the universe would eventually be found to share this strange duality, and the world would never look quite the same again. Imagine setting up a simple experiment. You place a light source at one end of a table, cut two narrow slits into a piece of cardboard, and position a screen behind it to catch whatever light passes through. It's almost absurdly simple, the kind of thing you might do in a physics class, and yet, in this humble arrangement, two holes and a beam of light, lies one of the most profound and unsettling experiments in all of science. The double-slit experiment has become legendary in physics, not because it's complicated, but because of what it reveals. Physicist Richard Feynman once said it demonstrated the central mystery of quantum mechanics, embodying the strange duality at the heart of the quantum world. The experiment was first performed in 1801 by English physicist Thomas Young, who used it to demonstrate the wave nature of light. Let's start with what we'd expect if we lived in a purely classical universe. Waves and particles behave very differently. If you send water waves through two openings in a barrier, they spread out, overlap, and create a pattern of peaks and troughs that reinforce or cancel each other. That's interference, and it's one of the clear signatures of wave behavior. Now imagine shooting tiny rubber balls at a wall with two openings. Some balls go through the left slit, some through the right. They don't overlap or interfere. On a screen behind the wall, you'd expect to see two bright clusters of impacts, one directly behind each slit. That's particle behavior, straightforward and predictable. So what happens when you shine light through two slits? When young and later, scientists performed this experiment, they expected light to behave like the wave it was thought to be, and it did. The light spread out, passed through both slits, and formed an interference pattern on the screen, a series of bright and dark bands caused by the waves overlapping and canceling each other in specific places. Young called these interference fringes. So far, so good. Light was behaving exactly like Maxwell had predicted, like an electromagnetic wave. But then things took a strange turn. Using very sensitive equipment, researchers turned down the intensity of the light until it was firing just one photon at a time. Instead of a continuous stream, individual particles of light made their way toward the slits, one by one, like solitary travelers. Now, you'd expect these lone photons to act like particles. Each one should go through one slit or the other and land on the screen directly behind whichever slit it passed through. If you wait long enough and collect enough hits, you should see two bright spots, just like with the rubber balls. But that's not what happened. Even when sent through one at a time, the photons gradually built up the same interference pattern as before, the striped pattern that requires waves interfering with themselves. It was as if each photon, traveling alone, somehow knew about both slits, as if it went through both slits at once, like a ghost exploring every possible path before finally landing somewhere on the screen. This was no illusion, no measurement error. The interference pattern persisted, clear and undeniable. It suggested that each photon, even a single one, was not simply a particle following a definite path. It was behaving like a wave that spread out and passed through both slits simultaneously, interfering with itself before collapsing into a single point of impact. But it gets stranger still. Physicists, naturally curious and slightly suspicious, decided to peek behind the curtain. They placed detectors at the slits to observe which path each photon actually took. Surely, they thought, we can just watch and settle this once and for all. Did the photon go through the left slit, the right slit, or somehow both? And this is where the universe revealed something truly unsettling. The moment the detectors were turned on, the interference pattern vanished. As soon as the photons were observed, they stopped behaving like waves. They acted like ordinary particles again, landing behind just one slit or the other. No more interference. No more ghostly wave behavior. It was as if the mere act of observing forced each photon to make a choice. Go left or go right, no superpositions, no fuzzy in-betweens. Turn the detectors off, and the interference returned. Turn them back on, and it disappeared again. The pattern held no matter how the experiment was modified. It wasn't that the measuring devices were clumsy or disturbed the photons physically. These were passive, non-intrusive setups. The issue wasn't how the observation was done, but that observation happened at all. Based on these results, it appears that the universe responds differently depending on whether information about the photon's path is potentially knowable. The act of observation, or even just the possibility of determining which path was taken, seems to be enough to collapse the photon's wave-like behavior into something definite. This wasn't a fluke or an experimental artifact. The double-slit experiment has been repeated countless times, with photons, electrons, atoms, and even large molecules. In fact, experiments have been performed with molecules containing over 800 atoms, and the results remain consistent with quantum predictions. The result is always the same. Left unobserved, these particles act like waves, spreading out and interfering with themselves. Observed, they behave like classical particles, falling neatly into line. If that sounds deeply unsettling, you're in good company. Niels Bohr, one of the founding figures of quantum mechanics, once said that anyone who isn't shocked by quantum theory hasn't understood it. The double-slit experiment sits at the very heart of quantum physics, and it resists every effort to explain it in comfortable, familiar terms. What the results suggest is that at the smallest scales, particles don't follow strict, predetermined paths. Instead, they exist as clouds of possibility, shimmering waves of potential outcomes. Only when a measurement is made does that cloud collapse into something definite, as though the universe, after considering all options, finally settles on one story to tell. Some physicists have tried to picture the photon as a wave that splits and then reunites, like a river flowing around an island. Others prefer the language of probability, describing the wave function as a mathematical tool for predicting where a particle might be found, not necessarily as a physical thing itself. Still others, in the many worlds camp, imagine that each possibility branches into its own separate universe, and that measurement simply selects which branch you find yourself in. But whatever the interpretation, the experimental facts remain stubbornly the same. Until we observe it, the particle doesn't commit to any one state. It hovers in a realm of many simultaneous possibilities, and it's only when we look, when we ask a question of the universe, that one of those possibilities becomes manifest in our experience. What began as a test of whether light was a wave has turned into a profound mystery about the nature of reality itself. Is observation an active part of shaping what we experience? Does information have power over what becomes actual? Is reality fundamentally uncertain until we ask it to reveal itself? These aren't just idle philosophical musings. They're questions rooted in hard, repeatable experiments. The double-slit experiment doesn't give us easy answers, but it does offer one powerful insight. The universe, at its core, is not a clockwork machine ticking away predictably in the background. It's a shimmering fabric woven from possibilities, and it responds, in curious and subtle ways, to our presence. With two slits, a light source, and a screen, we've discovered that the universe seems to behave one way when we're not looking, and another way when we are. And perhaps that's the most haunting part of all. Not that reality is uncertain, but that it waits quietly for us to ask. In the world of quantum physics, if there's one piece of mathematics that hums quietly through the entire theory like a secret melody, it's Schrödinger's equation. Now, don't worry, this won't be a lecture on differential equations or abstract operators. No one's getting out of bed to dream about calculus tonight. But this particular equation is different. It's not just a string of symbols scratched onto a chalkboard. It's the heartbeat of the quantum world, the rhythm that underlies everything from the glow of a firefly to the structure of atoms in your fingertips. Back in the 1920s, physicists were wrestling with a profound problem. Particles, like electrons, were showing wave-like patterns. Photons were acting like probabilistic ghosts. The old laws of motion, the ones Isaac Newton had given us centuries before, simply weren't cutting it anymore. The universe needed a new kind of language, a new way to describe how things moved and changed at the smallest scales. Enter Erwin Schrödinger. In 1925, he began working on the problem, and in 1926, he published an equation that described not just where a particle was or how fast it moved, but how its wave function evolved over time. It was elegant, compact, and shockingly effective. And even though it might look like a tangle of Greek letters to the uninitiated, at its core, it tells a simple story. It describes how quantum systems change moment by moment, how possibilities shift and ripple through the fabric of reality. The key concept here is the wave function, often represented by the Greek letter psi. Think of the wave function as a kind of mathematical whisper, a soft map of probabilities. It doesn't tell you exactly where a particle is. It tells you where it might be. It doesn't give you the particle's exact momentum. It gives you a range of possibilities. The wave function is a cloud of Mabes, a shimmering landscape of potential. In classical physics, if you want to describe a particle, you draw a neat arrow showing its exact position and velocity. Schrödinger's world doesn't allow that kind of certainty. Instead, it gives you a hazy, rippling cloud that says the particle is likely to be over here, but it could also be over there and maybe just a little bit up there too. This is where the power lies. Schrödinger's equation lets you evolve this cloud over time. It shows how the wave function changes as the system moves forward, though it's really more accurate to say how the possibilities of the system shift and flow. And when you measure the particle, when you ask the universe, "Where are you?" that wave function collapses. Suddenly, the cloud disappears, and you get a single, definite answer. Here it is, right here, but only after you've looked. This wave-based view of reality is profoundly different from the mechanical picture that came before. Instead of particles tracing predictable paths like planets orbiting the sun, we now see swirling fields of probability, full of uncertainty and ambiguity, only resolving into something concrete when observation forces them to choose. Let's make this more tangible. Imagine you're blindfolded and standing in a room. Somewhere in that room is a quiet cat. You can't hear it or see it, but you can toss small balls around and listen for the sounds they make when they land. Over time, you start to build a mental picture of where the cat might be. Some areas seem more likely than others. That mental map you're building, that's a bit like the wave function. It's not a picture of where the cat definitely is, but where it could be, weighted by likelihood. Now imagine you could write an equation that tells you how that map changes over time. Maybe the cat tends to move toward warm spots or corners. That equation would guide you toward where the cat is likely to be next. That's essentially what Schrödinger did, except instead of cats, he was thinking about electrons, and instead of guessing, he was calculating with extraordinary precision. The wave function is continuous and smooth. It ripples and shifts like water in a pond, obeying the symmetries of nature, respecting conservation laws, and evolving predictably according to the equation. But here's the catch. It doesn't tell you what will happen, only what could happen. And yet, despite this fundamental uncertainty, Schrödinger's equation works beautifully. Physicists have used it to describe everything from the structure of atoms to the way molecules bond, from semiconductor behavior to superconductors. It even predicts phenomena like quantum tunneling, where particles pass through barriers they classically shouldn't be able to cross, as though the walls of reality are just a little bit porous. One of the equation's greatest triumphs was explaining the hydrogen atom, the simplest atom in the universe. Before quantum mechanics, no one could fully explain why electrons around a nucleus seem to settle into specific energy levels, rather than spiraling inward or wandering off. Schrödinger's equation revealed that electrons aren't tiny planets whizzing around the nucleus. They form standing waves, stable patterns of probability that surround the nucleus in specific shapes. These are the orbitals you may have seen in textbooks, drawn as soft clouds or lobes around the center of an atom. They're not just visual aids. They represent the real measurable likelihood of where an electron might be found if you looked. These aren't orbits in the classical sense. They're regions of presence. zones where the electron's wave function has significant amplitude. It's strange, certainly, but it's also beautifully consistent. Schrödinger's equation has aged like fine wine. Unlike some theories that need patches or exceptions, this one just works. It has predicted, time and again, the behavior of the very small with astonishing accuracy. Schrödinger received the Nobel Prize in Physics in 1933 for this work, and yet it remains hauntingly abstract. You can't hold a wave function in your hand. You can't see it, but it's there, quietly describing the ghostly potential of everything from the air in your lungs to the silicon in your phone. Now let's turn to another cornerstone of quantum strangeness, the uncertainty principle. In the classical world, you can know where something is and how fast it's moving at the same time. There's no mystery, no contradiction. A radar gun clocks the speed of a car while GPS tells you exactly where it is. Easy. But the quantum world doesn't play by those rules. In 1927, Werner Heisenberg introduced a principle so strange and so central to quantum mechanics that it still gives students and seasoned physicists alike a moment of pause. It's called the Heisenberg uncertainty principle, and it tells us that at the most fundamental level of reality, there are limits to what we can know. Specifically, it says this: the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Momentum is just mass times velocity, a measure of how much motion something has. And if you think about it in everyday terms, this principle sounds absurd. How could knowing where something is make you unsure about how fast it's going? In the macroscopic world, this makes no sense. If you see a train pulling into a station, you know both its position and its speed. Simple, obvious. But at the quantum scale, reality doesn't allow that kind of clarity. Here's the key. This isn't about our measuring tools being clumsy or crude. It's not a matter of needing better technology. The uncertainty isn't in our instruments. It's woven into the fabric of the universe itself. Let's say you're trying to observe an electron. You want to know where it is and how fast it's moving. To do that, you might shine light on it. But light is made of photons, and photons carry energy and momentum. When one of those photons hits the electron, it changes the electron's motion. It's a bit like trying to find a soap bubble in the dark by throwing tennis balls at it. You'll definitely find it, but you'll also disrupt it in the process. But Heisenberg's point wasn't just about disturbing particles. His principle is built into the mathematics of quantum mechanics. Even in principle, if you could observe without physically disturbing the system, the uncertainty would still be there. It's not a bug, it's a feature of how wave functions work. At the heart of the uncertainty principle is the wave nature of particles. A particle like an electron is described by a wave function, a spread-out cloud of possibilities. If the wave is wide and smooth, you can't pinpoint where the particle is exactly, but you can estimate its momentum fairly well, because the wave has a well-defined wavelength. If you narrow the wave to pinpoint the particle's position, you need to add many different wavelengths together, which means the momentum becomes more uncertain. The wave gets choppy, unpredictable. It's a cosmic trade-off, and there's no way around it. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a tiny number. Planck's constant divided by 2. That number is very small, which is why in our everyday world, the effect is negligible. You can measure the position and speed of a baseball to incredible precision without ever bumping into quantum limits. But at the scale of electrons, atoms, and subatomic particles, the uncertainty becomes impossible to ignore. It shapes the very behavior of matter. If you try to confine a particle to very small space to pin down its position, it starts to behave energetically. Its momentum becomes highly uncertain, which means it could be moving in almost any direction at various speeds. Try to confine it further, and the energy required increases. It's as though nature doesn't like being told exactly where things are. This uncertainty also explains why atoms don't collapse. You might wonder why electrons don't simply fall into the nucleus, since opposite charges attract. But thanks to the uncertainty principle, electrons can't sit still. If an electron were to fall into the nucleus and stay there in a tiny, well-defined region, its position would be very precisely known, which means its momentum would become extremely uncertainty. That uncertainty translates to high kinetic energy. Nature says no to this infinite energy scenario, so electrons remain in their orbital clouds, not because they want to, but because quantum rules won't allow anything else. The uncertainty principle creates a kind of built-in resistance, a gentle pushback against absolute confinement, and this strange limit has consequences far beyond particle physics. It shows up in other pairs of properties too: energy and time, angular momentum, and orientation. In each complementary pair, increasing precision in measuring one quantity means surrendering certainty in the other. And yet, there's something almost comforting about it. Uncertainty, in this sense, is not chaos. It's not randomness run wild. It's a structured ambiguity, a kind of graceful fuzziness built into the quantum description of nature. It gives the universe texture. It allows particles to tunnel through barriers, atoms to remain stable, and chemistry to happen. Without it, reality might be too rigid to support the complex processes that make life possible. So much of science has been about finding certainty, about predicting, measuring, and knowing. Heisenberg's insight suggested that this quest has natural limits. He showed that some aspects of nature will always remain just out of reach. And that's not a failure of our methods. It's simply how things are at the quantum level. In a strange way, the uncertainty principle invites us to make peace with not knowing everything, to sit quietly with the blur and appreciate the softness of what lies beneath the surface. It's a reminder that the deepest truths are not always sharp-edged, but cloudy, rippling, and beautifully unresolved. And perhaps that's exactly why they're so compelling. In our everyday experience, things tend to be in one state or another. A coin lands heads or tails. A light switch is on or off. Your tea is hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division breaks down completely. Objects at the smallest scales don't always pick a side. They can exist in what physicists call a superposition, a blend of multiple possible states at once. This is one of the most counterintuitive ideas in all of physics. To picture this, imagine flipping a coin. In the classical world, once the coin leaves your hand, it travels through the air with a clear trajectory. You may not know whether it will land heads or tails until it settles, but throughout its flight, it is one or the other. The information is just hidden from you. Quantum systems don't work that way. If you could flip a quantum coin, it wouldn't be secretly one thing while you're not looking. Instead, it would enter a state of superposition, a mathematical combination of both heads and tails at once. It isn't undecided. It isn't switching rapidly between the two. According to quantum mechanics, it is genuinely in a state that embodies both possibilities simultaneously, until you observe it. And when you do, when you check to see what state the system is in, the superposition collapses. The quantum coin chooses a face, and your measurement yields a definite result. But before you looked, it wasn't just unknown. It was both. That's a hard concept to accept, and it's not just counterintuitive, it's profoundly strange. Superposition was developed as a way to describe the behavior of quantum particles like electrons and photons. These particles, rather than following predictable paths, are described by wave functions, mathematical expressions that encode probabilities. Each possible state, a spin pointing up or down, a photon traveling left or right, is part of the mathematical description. And all those possibilities coexist in the wave function until a measurement selects one. You might picture it like a foggy landscape of outcomes. The particle isn't walking a single definite path. It's more like it's spread out, exploring every possible route it could take simultaneously. When you interact with it and make a measurement, that fog suddenly snaps into focus, a single location or state illuminated, like lightning striking one hilltop in the mist. This concept led to one of the most famous thought experiments in all of physics, Schrödinger's cat. Erwin Schrödinger, the same physicist who gave us the wave equation, was deeply skeptical of how far some of his colleagues were willing to push the idea of superposition. In his view, there was something absurd about applying the same rules that governed electrons to everyday macroscopic objects like a living cat. So, in 1935, posed a provocative question designed to highlight what he saw as problems with the Copenhagen interpretation of quantum mechanics. Imagine a sealed box. Inside the box is a cat. Alongside the cat is a radioactive atom, a Geiger counter, a hammer or trigger mechanism, and a vial of poison. The setup works like this. If the atom decays, something quantum mechanics tells us happens probabilistically. The Geiger counter detects it, the trigger releases the hammer, the vial breaks, and the poison is released. The cat dies. If the atom doesn't decay within the allotted time, the cat lives. Here's where it gets strange. Quantum theory tells us that until the atom is observed, it exists in a superposition of both decayed and not decayed states, which means if we apply quantum mechanics to the entire system without exception, the whole setup, the detector, the poison mechanism, and yes, even the cat, should also be in a superposition. The cat would be both alive and dead at the same time, at least until someone opens the box and looks. Of course, no one has actually sealed a cat in a quantum box. Schrödinger wasn't proposing a real experiment or advocating for animal experimentation. He was making a philosophical point, a reductio ad absurdum argument aimed at the Copenhagen interpretation. He found it deeply troubling to think that a cat, a warm, living creature with a clearly defined state at any given moment, could exist in such a blurry, undefined superposition. To him, it highlighted a problem with applying quantum rules to macroscopic objects without qualification, and yet the image stuck. Partly because it captured the essence of quantum indeterminacy in a single, unforgettable scenario. A cat that is simultaneously alive and dead until the box is opened. That's a powerful way to express what it means for a system to remain unmeasured in quantum mechanics. Schrödinger's cat isn't really about cats. It's about what we're allowed to say about physical systems before we've made a measurement. In quantum mechanics, observation plays a central role. Before you measure a system, it exists as a wave function, a cloud of probabilities with each possible state encoded mathematically. But the moment you interact with it in a way that extracts information, that cloud collapses. The system manifests one definite state. One possibility becomes real in our experience. all others fade away. But here's where things get philosophically tricky. What exactly counts as a measurement? Is it the presence of a conscious observer? A mechanical detector? Any interaction with the environment? Different interpretations of quantum mechanics give different answers, and that ambiguity is part of why Schrödinger's cat still provokes discussion nearly a century later. Some physicists lean on the Copenhagen interpretation, which essentially says the wave function represents our knowledge of the system, and measurement reveals one of the possible outcomes without necessarily explaining the mechanism of collapse. Others prefer the many worlds interpretation, where the cat is both alive and dead, but in separate, non-communicating branches of reality. Opening the box doesn't collapse the wave function in this view. It merely determines which branch of reality you find yourself in. There's also the decoherence approach, which has gained significant traction in recent decades. This perspective argues that interaction with the environment naturally causes superpositions to become effectively classical. When a quantum system becomes entangled with many environmental degrees of freedom, air molecules, photons, thermal radiation, the superposition becomes practically inaccessible, even though technically the full quantum description still includes all possibilities. In this view, the cat is never truly in a limbo state because it's constantly interacting with its environment, which suppresses quantum interference effects. The superposition becomes invisible, not non-existent. Each perspective carries its own implications, but all agree on this: quantum systems do not behave like miniature classical objects, simply waiting to be discovered. They evolve probabilistically according to quantum rules in ways that often defy everyday intuition. So what does this mean for the cat? It suggests that the box isn't just a container. It represents a boundary between the quantum and classical worlds, a conceptual stage where the rules of physics take on stranger characteristics, where questions like, is the cat alive or dead, may not have definite answers until a measurement forces reality to commit. And that's what makes the cat such a perfect metaphor for unmeasured quantum systems. In the quantum realm, systems evolve according to Schrödinger's equation, but that evolution doesn't pick a single path. It encompasses all possible paths simultaneously. An electron doesn't travel from point A to point B along one route. It explores every route, every possibility, until we observe it and that exploration collapses into a single definite outcome. The cat in the box is just a macroscopic, dramatic way of expressing that reality. The difference between a cat and an electron is one of scale and complexity, not necessarily a fundamental principle. And that's what troubled Schrödinger. If quantum theory truly applies universally, then at some level, everything could be considered part of quantum superpositions. This raises one final, somewhat unsettling question. What if the observer is part of the system? If opening the box collapses the cat's wave function, what collapses the observer's wave function? Where does the chain of observation end? These questions remain at the heart of ongoing debates about quantum measurement and the nature of reality. In the end, Schrödinger's cat isn't just about life and death. It's about knowledge and the intricate relationship between reality and observation. It's about what it means to say something is when the very act of determining that might influence the outcome. It's a reminder that in the quantum world, certainty is rare, clarity is conditional, and sometimes the universe genuinely seems to wait for us to peek inside the box before committing to an answer. Despite its philosophical weight, superposition isn't just an abstract thought experiment. It has real, practical applications that are shaping modern technology. Take quantum computing, for instance. In a classical computer, The smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every song, every photo, every message is encoded using combinations of these two definite states. Quantum computers use qubits instead, and a qubit, unlike a regular bit, can exist in a superposition of both 0 and 1 at the same time. It's not switching between them, it's genuinely in a mathematical mixture of both. This means a single qubit can, in a sense, represent more information than a classical bit. And when multiple qubits are entangled together, they can represent a vast number of states simultaneously. This allows quantum computers to explore many possible solutions to certain problems at once, potentially making them far more efficient than classical computers for specific tasks. It's not magic. It's mathematics that plays by quantum rules. Problems involving complex optimization, simulating quantum systems like molecules, or searching through vast datasets could potentially become more tractable. And it all hinges on the ability of qubits to exist in superposition. Superposition also plays a role in quantum cryptography, where it helps ensure that information can't be intercepted without detection. In quantum sensing, superpositions allow scientists to detect extremely small changes in magnetic fields, gravitational fields, or other physical quantities with unprecedented precision. These aren't science fiction fantasies. They're real technologies being developed and refined right now, all resting on the strange foundation of quantum superposition. But there's a significant catch. Superposition is extraordinarily delicate. Quantum systems are easily disturbed. The slightest uncontrolled interaction with the environment, stray photons, vibrations, thermal fluctuations, even nearby air molecules, can cause the wave function to decohere. This process, known as decoherence, is one of the biggest challenges in building stable quantum systems. It's like trying to balance a feather on the tip of a needle while someone's playing drums in the next room. The superposition vanishes the moment the system couples significantly with its surroundings. That fragility is part of what makes quantum systems so fascinating and challenging. They offer remarkable computational power and sensing capabilities, but only under very precise, carefully controlled, and isolated conditions. They give us access to probabilities and interference effects, not deterministic certainties, and they ask us to fundamentally rethink what it means to say that something exists in a definite state. Quantum superposition invites us to loosen our grip on classical either-or logic. It suggests that opposites can coexist, that a system can embody multiple contradictory states simultaneously, and that reality at its core is not a single thread, but a rich fabric woven from overlapping possibilities, unresolved until observation or interaction singles out one strand. It's strange, it's uncomfortable, but it's also beautiful, because in this peculiar rule of superposition, we find a universe that isn't rigid but flexible, not mechanical but fluid. It's a reality that allows for ambiguity and multiplicity, not as flaws but as fundamental features. First, and in doing so, it opens up new ways to compute, to communicate, to explore, and to imagine what becomes possible when the universe refuses to commit to a single answer until asked. Imagine you have two gloves, one left-handed and one right-handed. You put each glove into a separate box and send one box halfway across the world. You don't know which box contains which glove, but the moment you open your box and see a left-handed glove, you instantly know the other box must contain the right-handed one. It's not mysterious, it's just logic and conservation. The gloves were always one left, one right, determined from the start. No drama there. But quantum entanglement isn't like that. Entangled particles aren't like pre-sorted gloves. They're more like a pair of gloves that genuinely don't have a definite handedness until you open one of the boxes. And whichever one you open first, the measurement you make on it somehow correlates instantly with what the other becomes, no matter how far apart they are. It's not just that the outcomes are correlated. It's that, according to quantum mechanics, the properties don't exist in definite states until the moment one of them is measured. And the act of measuring one particle instantly determines the measurement outcome for the other. This is the phenomenon of quantum entanglement, and it is one of the strangest, most philosophically provocative features of the quantum world. Here's how it works. When two particles interact in certain ways, by being created together in a decay process, colliding, or otherwise becoming correlated through quantum interactions, they can become entangled. That means their quantum states become intrinsically linked. What happens to one particle, in a very real sense, appears to be instantly correlated with what happens to the other, even when they're separated by enormous distances. Imagine creating two entangled photons whose polarizations are correlated but individually uncertain until measured. According to quantum mechanics, before measurement, neither photon has a definite polarization. They exist in a shared entangled state. When you measure one photon and find it vertically polarized, the other photon's wave function instantly becomes horizontally polarized, or whatever the correlation dictates. No signal travels between them. If you measure one photon in Paris, the other, even if it's in Tokyo, will show the correlated result the instant you check it, as though the universe updated both of them simultaneously. This is what Albert Einstein famously called spooky action at a distance. Einstein wasn't fond of spooky things. He believed firmly in locality, the principle that physical processes at one location can't instantly affect things far away. It's a cornerstone of relativity theory. Nothing, not even information, can travel faster than the speed of light. The idea that two particles could coordinate outcomes instantaneously without exchanging any signal made him deeply uncomfortable. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that challenged the completeness of quantum mechanics. They argued that if quantum mechanics predicts such instantaneous correlations, it must be missing something. Perhaps there were hidden variables, properties determined from the start but unknown to us, that would explain the correlations without requiring faster-than-light influences. To Einstein, the universe should be predictable, orderly, and perhaps most importantly, local. But decades later, experiments began to test these ideas directly. In 1964, physicist John Bell devised a mathematical framework, now known as Bell's theorem, that could distinguish between quantum mechanical predictions and theories based on local hidden variables. Bell showed that if local hidden variables existed, certain statistical correlations between measurements would have to satisfy specific inequalities, now called Bell's inequalities. But quantum mechanics predicted violations of those inequalities. When physicists performed the experiments, starting with pioneering work by a LAN aspect in the early 1980s and continuing with increasingly sophisticated setups, quantum mechanics won. Again and again, the results violated Bell's inequalities exactly as quantum theory predicted. The correlations were stronger than any local hidden variable theory could explain. Entangled particles truly do behave in ways that can't be explained by assuming they carry predetermined properties from the moment they separate. More recent experiments have closed various potential loopholes, including the locality loophole and the detection loophole, making the results even more definitive. The results appear random at each location, yet perfectly correlated across space. It's as if the particles share a script that remains unwritten until one of them is measured, and then both improvise together with eerie, perfect coordination. Still, this doesn't mean you can use entanglement to send messages faster than light. That would violate causality. And thankfully, nature prevents it. While entangled particles show instant correlations in their measurement outcomes, those outcomes are fundamentally random. You can't control what result you get when you measure your particle, which means you can't encode information that could be read at the distant location. The correlation is real, but it can't be exploited for communication. It's like two people flipping coins on opposite sides of the galaxy. Each result is random, but somehow, when one person flips heads, the other always flips tails. Neither knows which outcome they'll get until they flip. They aren't sending messages. They're just mysteriously synchronized in a way that transcends space. What's truly remarkable is that this connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent, or a light year, and the entanglement would persist. There's no known limit. In fact, physicists have demonstrated entanglement over distances exceeding 1,200 kilometers using satellites, and the correlations continue to uphold quantum predictions. But what exactly is entanglement? Is it a kind of invisible thread connecting the particles? A shared identity stretched across space? A form of information distributed between them? The truth is, we're not completely sure. Different interpretations of quantum mechanics offer different perspectives. Some view entanglement as information, what we know about the correlations between systems, rather than something physically connecting them. Others see it as evidence of a deep, non-local aspect woven into the fabric of reality itself. There's even emerging theoretical research suggesting that entanglement might not just be a quirky quantum phenomenon, but a fundamental feature related to space-time geometry itself. Some theoretical physicists have proposed that space-time, the very structure of the universe, might emerge from networks of quantum entanglement between microscopic degrees of freedom. If this perspective holds, entanglement isn't just something that happens in space. It could be part of what creates the structure of space in the first place. That's a speculative idea still being explored, but it suggests how deeply entanglement might be woven into reality. Entanglement has practical applications too. Quantum cryptography relies on entangled particles to create secure communication channels. If someone tries to intercept an entangled quantum signal, the entanglement breaks, and both parties know immediately that someone was listening. It's security built on the fundamental laws of physics, impossible to bypass without detection. Entanglement is also being explored for quantum teleportation, not the science fiction kind where you beam people across space, but a process where quantum information is transferred from one location to another using entangled particles as a bridge. The original particle's quantum state is destroyed in the process, but its information appears at the destination. It's strange, elegant, and completely within quantum rules. Perhaps the most profound aspect of entanglement is what it reveals about reality itself. The universe, at its deepest level, isn't made of isolated, independent objects, bumping into each other like billiard balls. It's a web of relationships, connections that transcend distance and persist regardless of separation. Particles that have interacted remain, in some sense, part of a larger unified system. They share a story that continues to unfold together, even when the chapters are written light years apart. Einstein once hoped to prove that quantum mechanics was incomplete, that beneath the probabilistic surface there was a deterministic reality waiting to be uncovered. But experiment after experiment has shown that the spooky action is real. The universe doesn't need hidden variables to explain its behavior. It's genuinely, irreducibly strange, and maybe that's okay. Maybe the universe doesn't owe us the comfort of locality. Maybe distance is just one way of organizing experience, but not the deepest truth. Entanglement suggests that separation is in some ways an illusion, or at least superficial. What looks like two particles separated by vast stretches of space might actually be one quantum system, stretched across the cosmos, still performing its intricate dance to a rhythm set when they first interacted. It's a reminder that the boundaries we draw between here and there, between self and other, between observer and observed, may be less fundamental than they appear. In the quantum world, everything touches everything else, not through force or signal, but through a kind of intimate correlation that defies simple explanation and invites endless wonder. And in the quiet hours of the night, when you look up at the stars and feel impossibly far from them, remember this: at the quantum level, distance becomes negotiable. Connection is fundamental. And somewhere across the vastness of space, particles that were once together still remember each other, responding instantly, as though no time or distance had ever come between them. In the classical world, if you throw a ball at a wall, it bounces back. If the ball doesn't have enough energy to break through, it simply doesn't get to the other side. Simple. Obvious. Walls are solid barriers, and energy is required to overcome them. That's just how things work. But in the quantum world, particles don't always respect those rules. Sometimes they pass through barriers they shouldn't be able to cross. They don't smash through. They don't climb over. They simply appear on the other side, as though the wall were just a suggestion rather than an absolute obstacle. This phenomenon is called quantum tunneling, and it's one of the most remarkable and practically important aspects of quantum mechanics. Here's how it works. In quantum mechanics, particles are described by wave functions, which spread out and represent probabilities. When a particle encounters a barrier, an energy hill, it doesn't have enough energy to climb classically. The wave function doesn't just stop abruptly. It extends into and through the barrier, diminishing in amplitude but not disappearing entirely. On the other side of the barrier, there's a small but non-zero probability that the particle will be found there. It's as though the particle is testing every possible path, and some of those paths, improbable as they might be, lead directly through the barrier. When a measurement is made, when reality commits to an outcome, the particle might just end up on the other side, having tunneled through a wall it classically had no business crossing. This isn't a rare or exotic phenomenon. It happens constantly, all around us, in ways both subtle and profound. Quantum tunneling is responsible for the sun shining, for radioactive decay, for the operation of modern electronics, and for chemical reactions happening inside your cells right now. Let's start with the sun. At the core of our star, hydrogen nuclei are being fused into helium, releasing enormous amounts of energy in the process. But there's a problem. For fusion to occur, two hydrogen nuclei, both positively charged protons, need to get close enough for the strong nuclear force to bind them together. The trouble is, like charges repel, the electrical repulsion between the protons creates an energy barrier. In a purely classical universe, the hydrogen nuclei at the sun's core wouldn't have enough thermal energy to overcome that barrier. They'd bounce off each other, and fusion wouldn't happen. The sun wouldn't shine. Life on Earth wouldn't exist. But thanks to quantum tunneling, the nuclei don't need to climb over the barrier. They can tunnel through it. The wave function of each nucleus extends slightly beyond the barrier, and there's a probability that they'll find themselves close enough for the strong force to take over and bind them together. It's a low probability event for any individual pair, but with countless trillions of collisions happening every second, tunneling occurs often enough to keep the sun burning steadily for billions of years. Without quantum tunneling, stars wouldn't ignite. The universe would be cold, dark, and lifeless. Every photon that warms your skin, every sunrise, every flicker of starlight in the night sky exists because particles can slip through barriers they classically shouldn't be able to cross. Quantum tunneling also plays a central role in radioactive decay. Some atomic nuclei are unstable, containing particles that are bound but not quite securely enough. Classically, those particles should remain trapped. They don't have enough energy to escape. And yet, given enough time, they do escape. They tunnel through the energy barrier that confines them, and the nucleus decays, releasing radiation in the process. The probability of tunneling determines the half-life of radioactive elements. Some decay quickly, tunneling through in seconds. Others take billions of years, but in every case, the mechanism is the same. A particle confined in a potential well that shouldn't be able to escape, managing to do so because the quantum world allows for possibilities that the classical world forbids. Quantum tunneling isn't just theoretical, it's been harnessed in technology. One of the most elegant examples is the Scanning Tunneling Microscope, or STM, a device that uses quantum tunneling to image surfaces at the atomic level. And STM works by bringing a sharp metal tip very close to a surface, close enough that electrons can tunnel between the tip and the surface. No physical contact is made, but a small voltage applied between the tip and surface allows a tunneling current to flow. The current is exquisitely sensitive to the distance between the tip and the surface. Change the distance by even a fraction of an atomic diameter, and the current changes dramatically. By scanning the tip across the surface and measuring how the tunneling current varies, scientists can map out the positions of individual atoms. This technology has allowed researchers to see atomic structures directly, to move individual atoms around, and to study surfaces in ways that were unimaginable just a few decades ago. The inventors of the STM, Gerd Binnig and Heinrich Rohrer, received the Nobel Prize in Physics in 1986 for this groundbreaking work. It's a direct application of quantum tunneling, turning a strange quantum effect into a powerful tool for exploring the nanoscale world. Tunneling also appears in biology, though this is a more recent and still developing area of research. Enzymes, the molecular machines that facilitate chemical reactions in living organisms, sometimes appear to rely on quantum tunneling to transfer protons or electrons across energy barriers. This allows reactions to proceed much faster than they would if particles had to classically overcome those barriers. In some cases, evidence suggests that enzymes may have evolved to enhance tunneling probabilities, optimizing their structure to make quantum effects more likely. There's growing evidence that quantum tunneling plays a role in processes as fundamental as cellular respiration and DNA repair. The idea that quantum mechanics isn't just relevant at the level of isolated atoms, but plays a functional role in the warm, wet, messy environment of living cells is part of an emerging field called quantum biology. It's still early days, and many claims remain under investigation, but the evidence is accumulating that life may have found ways to exploit quantum phenomena that we're only beginning to understand. Now, let's talk about the quantum vacuum, one of the strangest ideas in all of physics. In classical terms, a vacuum is simply empty space, a region with no matter, no energy, nothing. But in quantum mechanics, there's no such thing as truly empty space. Even in a perfect vacuum with no particles present, quantum fields are constantly fluctuating. These fluctuations arise from the uncertainty principle. Remember that uncertainty applies not just to position and momentum, but to energy and time as well. Over very short timescales, energy can fluctuate wildly. Pairs of particles and antiparticles can pop into existence out of nothing, live for a brief moment, and then annihilate each other, disappearing back into the vacuum. These are called virtual particles. And while the term can be misleading, they're not directly observable as particles in the usual sense. They have measurable effects on real physical systems. One of the most famous is the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force. This force arises because the vacuum fluctuations between the plates are restricted. Only certain wavelengths fit in the narrow gap, while outside the plates, the full spectrum of fluctuations is present. The difference in vacuum energy density creates a net force pushing the plates together. The Casimir effect has been measured experimentally with high precision, confirming that the quantum vacuum isn't empty at all. It's a seething, bubbling sea of potential where quantum fluctuations occur constantly. Virtual particles also affect the properties of real particles. Electrons, for example, are constantly surrounded by a cloud of virtual photons and particle-antiparticle pairs that pop in and out of existence around them. These interactions slightly alter the electron's energy and other properties, effects that have been measured with extraordinary precision and match quantum field theory's predictions almost perfectly. The idea that empty space is full of energy has profound implications. Some physicists have speculated about connections between vacuum energy and dark energy, the mysterious force causing the universe to expand at an accelerating rate. The connection isn't straightforward, though. When you calculate the energy density of the quantum vacuum using quantum field theory, you get a number that's vastly, absurdly larger than the observed value of dark energy, by a factor of about 10 to the power of 120, one of the largest discrepancies in all of physics. This is known as the cosmological constant problem, and it remains one of the deepest unsolved puzzles in theoretical physics. The fact that we don't understand why the vacuum energy is so much smaller than predicted doesn't change the experimental reality. The vacuum has energy, structure, and consequences. Nothingness at the quantum level is actually something. Quantum tunneling and the quantum vacuum remind us that the boundaries we take for granted, solid walls, empty space, the distinction between something and nothing, are softer and more permeable than they appear. Particles slip through barriers that should be impenetrable. Energy emerges from emptiness. The universe, at its smallest scales, is constantly surprising us, constantly defying our everyday intuitions. And perhaps that's the real gift of quantum mechanics. It doesn't just give us new tools or new technologies, though those are valuable. It gives us a new way of seeing. It teaches us that reality is not fixed or certain, that the rules we thought were absolute have exceptions, and that even in the darkest, most silent void, there is activity, potential, and possibility. Tunneling allows stars to shine. The vacuum hums with invisible energy, and somewhere in the quiet spaces between particles, the universe is doing something we don't quite understand yet, something strange and beautiful and worth wondering about as we drift toward sleep. By now, you've journeyed through some of the strangest landscapes in physics. You've seen particles that behave like waves, measurements that collapse possibilities into certainties, and connections that span distances instantaneously. You've learned about uncertainty, superposition, and the blurry line between what is and what might be. But there's one question we haven't fully addressed yet, perhaps the deepest and most unsettling question of all. What does it all mean? What is quantum mechanics actually telling us about reality? Is the wave function a real physical thing, or just a mathematical tool for calculating probabilities? When a measurement collapses a superposition, is something actually happening in the universe? Or are we just updating our knowledge? And perhaps most provocatively, does reality even exist in a definite state when no one's looking? These aren't idle questions. They strike at the heart of what it means to do science, to understand the world, and to trust that the universe has an objective existence independent of our observations. Physicists, philosophers, and curious minds have been debating them for nearly a century. Let's explore some of the major interpretations of quantum mechanics, each offering a different answer to the question of what the theory is really saying. The Copenhagen interpretation is the oldest and perhaps still the most widely taught view of quantum mechanics. It was developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, and it became something of an orthodoxy for decades. According to the Copenhagen interpretation, the wave function is a tool for predicting measurement outcomes, not necessarily a description of an objective reality existing between measurements. Before you measure a particle's position, the interpretation suggests it doesn't have a definite position in the classical sense. It exists in a superposition of possibilities. The act of measurement causes the wave function to collapse, selecting one outcome from the range of possibilities, and that outcome becomes manifest in our experience. In this view, asking what the particle is doing when you're not looking is often considered a meaningless or at least unanswerable question. Quantum mechanics tells you what you'll observe when you make a measurement, and that's what matters for making predictions. The theory doesn't necessarily describe an underlying reality independent of observation. It describes the relationship between observers and quantum systems. This interpretation has a certain pragmatic appeal. It sidesteps difficult metaphysical questions about what's really happening by focusing on what can be observed and predicted. It works brilliantly for doing calculations, making predictions, and designing experiments. But it also leaves many people feeling unsatisfied. If the wave function collapses when a measurement is made, what exactly counts as a measurement? Does it require a conscious observer? A mechanical detector? Any interaction with the environment? The Copenhagen interpretation doesn't give a completely clear answer, and that ambiguity has troubled physicists and philosophers for decades. Einstein famously disliked the Copenhagen view. His objection wasn't that it made wrong predictions, but that it seemed to give up on the idea of an objective reality existing independent of observation. Do you really believe the moon isn't there when you're not looking at it? He once asked Abraham Pais. For Einstein, the universe should have definite properties, whether or not anyone is observing them. The many worlds interpretation in 1957, physicist Hugh Everett proposed a radically different interpretation that has gained significant popularity in recent decades, especially among physicists working in quantum computing, quantum information, and cosmology. It's called the many worlds interpretation, and it solves the measurement problem in a bold and strange way. It says there is no collapse. According to many worlds, when a quantum system is in a superposition, all possible outcomes are equally real. When you measure a particle's spin and find it pointing up, there's another version of you in another branch of reality who measured it pointing down. Both outcomes happen. The universe splits, or more accurately, continuously branches into parallel versions, one for each possible quantum outcome. In this view, the wave function never collapses. It keeps evolving smoothly according to Schrödinger's equation. What we experience as a measurement is simply the universe branching into multiple, non-interacting worlds, each containing a version of us who observed a different outcome. This interpretation is elegant in some ways. It doesn't require any special collapse mechanism. It treats observers as just another part of the quantum system, governed by the same laws. And it explains why we only see one outcome. We're in one branch, unaware of all the other versions of ourselves in parallel branches, experiencing different results. But it comes with a hefty ontological price. It requires accepting that countless parallel universes exist, that every quantum decision spawns new realities, and that an unimaginable number of versions of you are living out every possible variation of your life. Many find this extravagant, even if it's mathematically consistent. The many worlds interpretation also raises questions about probability. If all outcomes happen, why do we observe some more frequently than others? Proponents have developed answers involving the measure of different branches and how they relate to the Born rule, but the interpretation remains philosophically contentious. Still, for those comfortable with its implications, Many Worlds offers a deterministic, collapse-free view of quantum mechanics where the only strangeness is that everything that can happen does happen somewhere in the multiverse. Another interpretation, less well known but enjoying a revival of interest, is pilot wave theory, also called de Broglie-Bohm theory or Bohmian mechanics, originally proposed by Louis de Broglie in the 1920s and later developed by David Bohm in the 1950s. This interpretation takes a different approach entirely. Pilot wave theory says that particles do have definite positions and velocities at all times, even when not being measured. But they're guided by a real physical wave, the wave function itself, that evolves according to Schrödinger's equation. The particle surfs along this wave field, which determines its trajectory. In this view, the wave function is a real field, similar to an electromagnetic field, and particles follow paths determined by the shape and flow of that field. The apparent randomness in quantum mechanics comes from our ignorance of the particle's precise initial conditions, not from any fundamental indeterminacy. This interpretation is explicitly non-local. The pilot wave for a particle can be affected instantaneously by distant events, which explains entanglement without requiring faster-than-light signaling. It restores determinism and gives particles definite properties at all times, which appeals to those uncomfortable with the Copenhagen view's observer dependence. However, pilot wave theory is also more complex mathematically, and it introduces elements, like the guiding wave, that can't be directly observed separate from their effects on particles. Many physicists find it less elegant than other interpretations, though its recent resurgence suggests that some are willing to trade simplicity for a more intuitively realistic picture. A more modern perspective focuses on decoherence, the process by which quantum systems lose their coherence and start to behave classically due to interactions with their environment. When a quantum system becomes entangled with many environmental degrees of freedom, air molecules, photons, thermal radiation, the superposition effectively becomes inaccessible. The system appears to have collapsed into one state, even though technically the full quantum description still includes all possibilities spread across the larger environment. Decoherence helps explain why we don't see macroscopic superpositions, why cats aren't both alive and dead. Living systems are constantly interacting with their warm, complex environments, which suppresses quantum interference effects extraordinarily quickly. Decoherence doesn't fully solve the measurement problem by itself. It explains why superpositions become practically unobservable, but doesn't completely explain why we experience one particular outcome rather than another. Still, it's a crucial piece of the puzzle and helps bridge the gap between quantum and classical worlds. One of the more controversial ideas is that consciousness might play a role in collapsing the wave function. This view suggests that it's the presence of a conscious observer that turns quantum possibilities into classical realities. Some physicists, like John von Neumann and Eugene Wigner, explored this idea seriously in the mid-20th century. The basic notion is that the chain of quantum entanglement between a measured system and measuring apparatus needs to terminate somewhere, and perhaps conscious awareness provides the termination point. However, this interpretation faces significant challenges. It raises questions about what counts as conscious, whether animals or computers can collapse wave functions, and how consciousness, if it's fundamentally different from physical processes, could interact with physical systems. Most physicists today are skeptical of consciousness-based interpretations, preferring explanations that don't require invoking subjective experience as a fundamental physical principle. The relationship between quantum mechanics and consciousness remains a topic of philosophical interest and some scientific investigation, but mainstream physics generally doesn't rely on consciousness to explain quantum phenomena. So where does this leave us? After a century of quantum mechanics, we still don't have a universally agreed upon answer to the question of what the theory means. Different interpretations make the same predictions for experiments, so we can't simply test which one is right through measurement alone. Choosing between them often comes down to philosophical preferences, aesthetic judgments, or what kinds of questions you think science should be able to answer. Some prefer the minimalism of Copenhagen. Focus on predictions, don't worry about metaphysics. Others want the concrete reality of pilot wave theory or the sweeping comprehensiveness of many worlds. Still others hope for new physics that will eventually clarify what quantum mechanics is really telling us. Perhaps the most honest answer is that we don't know yet. Quantum mechanics is astonishingly successful at predicting the behavior of the physical world, but the interpretation, the story we tell about what's really going on beneath the mathematics, remains open, and maybe that's okay. Maybe the universe is under no obligation to match our intuitions or fit neatly into our conceptual categories. Maybe reality is genuinely stranger than we can imagine, and quantum mechanics is just the beginning of understanding how strange it really is. What we do know is that the quantum world challenges our deepest assumptions about existence, observation, and the nature of reality. It invites us to question whether the universe is fundamentally continuous or discrete, deterministic or probabilistic, local or non-local, objective or observer-dependent. And in the quiet hours, when the day's certainties have faded and the mind drifts towards sleep, perhaps the ambiguity is a gift. Perhaps not knowing the ultimate answer allows us to hold multiple possibilities at once, to remain open, curious, and humble before the mystery. The universe doesn't owe us explanations, but it does offer endless invitations to wonder. We've journeyed through the birth of quantum thinking, through the strangeness of superposition and entanglement, through tunneling and interpretations. Now, as our exploration draws toward its close, let's look at how quantum mechanics has expanded beyond the atom, shaping technology, suggesting connections to biology, and continuing to reshape our understanding of the cosmos and our place within it. As quantum mechanics matured through the mid-20th century, physicists realized that a complete theory needed to account not just for particles, but for the forces between them, and for the fact that particles can be created and destroyed. This led to the development of quantum field theory, a framework that treats particles not as fundamental objects themselves, but as excitations, ripples, or vibrations in underlying quantum fields. Think of it like this. Imagine the universe is filled with invisible fields, one for each type of particle: the electron field, the quark field, and so on. These fields exist everywhere, pervading all of space. When a field is excited, when it ripples or vibrates in a particular way, we observe what we call a particle. An electron is a localized excitation in the electron field. A photon is an excitation in the electromagnetic field. This perspective resolves many puzzles. It explains how particles can appear and disappear, how energy can be converted into matter and back again, and how forces are transmitted through the exchange of force-carrying particles. Quantum field theory became the foundation for the standard model of particle physics, one of the crowning achievements of 20th century science. The standard model describes three of the four fundamental forces: electromagnetic, weak, and strong, and catalogs the elementary particles that make up all matter. It includes quarks, the building blocks of protons and neutrons, leptons, like electrons and neutrinos, and bosons, the force-carrying particles. Photons carry the electromagnetic force, W and Z bosons carry the weak force, and gluons carry the strong force. At the heart of the model is the Higgs field, which gives particles their mass through their interactions with it. The existence of the Higgs boson, the particle associated with the Higgs field, was predicted decades before it was finally discovered in 2012 at the Large Hadron Collider at CERN. That discovery was a triumph, confirming the last missing piece of the standard model and validating decades of theoretical work. And yet, despite its extraordinary success, the standard model is known to be incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy, which together make up roughly 95% of the universe's mass energy content. It doesn't tell us why the fundamental constants have the values they do, or why there are exactly 3 generations of particles. These gaps suggest that there's more to discover, that quantum field theory, as powerful as it is still only part of a larger story. Physicists are exploring theories beyond the standard model, including supersymmetry, string theory, and new approaches to quantum gravity. The quest continues, driven by the same curiosity that first led Planck to introduce quanta more than a century ago. Beyond fundamental physics, quantum mechanics is driving a technological revolution. Quantum computing, once a purely theoretical idea, is becoming a tangible reality with potentially transformative applications. Classical computers process information in bits, which are either 0 or 1. Quantum computers use qubits, which can exist in superpositions of both states at once. This allows quantum computers to explore many possibilities simultaneously, making them potentially much faster for certain types of problems. Quantum computers could revolutionize cryptography, both by breaking current encryption methods and by enabling new quantum-secure communication protocols. They could simulate complex molecules with high fidelity, accelerating drug discovery and material science. They could optimize logistics, financial modeling, and machine learning in ways classical computers struggle with. As of 2026, major technology companies and research institutions continue to make significant progress in building practical quantum computers. Recent developments include advances in error correction, improved qubit coherence times, and the integration of quantum systems into cloud computing platforms. While substantial challenges remain, particularly around maintaining quantum coherence and scaling up systems, the field is moving steadily from laboratory demonstrations toward commercially relevant applications. Quantum key distribution is entering the realm of photonic integrated circuit chips, and there's increasing interest in quantum networks for distributed quantum computing and long-distance secure communications. These developments suggest that 2026 marks a period of genuine progress toward quantum industrialization, with both digital and analog quantum processing units advancing alongside improvements in hybrid quantum classical architectures. Beyond computing, quantum technologies are emerging in sensing, imaging, and measurement. Quantum sensors can detect gravitational waves, map magnetic fields with unprecedented precision, and measure time with extraordinary accuracy. These applications rest on the same quantum principles we've explored: superposition, entanglement, and interference, turning abstract theory into concrete tools that extend human capability. One of the most surprising and exciting frontiers is quantum biology, the study of whether quantum effects play functional roles in living organisms. For a long time, it was assumed that quantum mechanics was irrelevant to biology. Living systems are warm, wet, and complex conditions that typically destroy quantum coherence almost instantly. But recent research has found intriguing hints that nature may be exploiting quantum phenomena after all. Photosynthesis, the process plants use to convert sunlight into chemical energy, is remarkably efficient. Some studies have suggested that quantum coherence might help energy transfer through photosynthetic complexes, allowing plants to explore multiple pathways simultaneously and find the most efficient routes for moving energy. However, this remains a topic of active research and some debate. The evidence suggests quantum effects may contribute, but the extent and mechanisms are still being investigated, and distinguishing quantum effects from classical phenomena in warm biological systems is extraordinarily challenging. Enzymes, the molecular machines that catalyze reactions in cells, appear to use quantum tunneling to speed up reactions, particularly those involving hydrogen or electron transfer. Experiments show that tunneling allows particles to pass through energy barriers much faster than classical physics would predict, enhancing enzyme efficiency. There's also research exploring whether birds might use quantum processes in specialized proteins in their eyes to sense Earth's magnetic field for navigation, though this too remains an area of ongoing investigation. DNA repair mechanisms may involve quantum tunneling as well. The field of quantum biology is young, and many claims are still speculative. Distinguishing quantum effects from classical phenomena in warm, noisy biological systems is extraordinarily difficult. But the possibility that life, in its intricate complexity, has found ways to exploit quantum mechanics, it suggests that the boundary between the quantum and classical worlds isn't as sharp as we once thought, and that nature, through billions of years of evolution, may have discovered quantum technologies long before we did. Quantum mechanics doesn't just describe atoms and particles. It has profound implications for cosmology, the study of the universe as a whole. The early universe, moments after the Big Bang, was a quantum system, tiny quantum fluctuations in the fabric of space-time itself, amplified by a period of rapid expansion called cosmic inflation, are thought to have seeded the formation of galaxies, stars, and planets. Every large-scale structure in the universe, including the very place you're resting right now, may trace its origin to quantum uncertainty in the first fractions of a second after the universe began. Quantum mechanics also raises deep questions about the ultimate fate of information, the nature of black holes, and the possibility of multiple universes. These questions sit at the intersection of quantum theory and gravity, a frontier where our current understanding breaks down and new physics is needed. Some physicists have proposed that space and time themselves might be emergent properties arising from deeper quantum structures or networks of entanglement. Others explore whether the universe behaves like a quantum information processor of sorts, with information playing a fundamental role. These ideas are highly speculative, but they reflect the ongoing effort to understand how quantum mechanics fits into the largest possible picture of reality. As we near the end of this journey, let's step back and reflect on what quantum mechanics has taught us, not just about physics, but about existence itself. Quantum mechanics tells us that the universe is not a machine. It's not deterministic in the way Newton imagined. At its core, reality is probabilistic, uncertain, and observer-entangled in ways that challenge our deepest intuitions. It tells us that observation matters. The act of measuring something changes our relationship to it and perhaps even influences what becomes manifest. Reality doesn't exist in neat prepackaged facts, waiting passively to be discovered. It unfolds through interactions between systems and measurements, a dance between possibility and actuality. It tells us that connection runs deeper than separation. Entangled particles remain correlated across space, suggesting that the boundaries we draw between here and there, between self and other, may be less fundamental than they appear. And it tells us that certainty is a luxury, not a given. The Heisenberg uncertainty principle isn't a limitation of our knowledge or tools. It's a statement about the nature of reality. Some things simply cannot be known simultaneously with arbitrary precision, and that's woven into the fabric of existence. The universe doesn't owe us complete information. In many ways, quantum mechanics is a lesson in humility. It reminds us that our everyday experience, the world of solid objects and predictable outcomes, is just one layer of reality. Beneath it lies a stranger, softer world, where possibilities shimmer and certainty dissolves. But it's also a lesson in wonder, the fact that particles can be waves, that the vacuum hums with invisible energy, that observation seems to shape what becomes real. These aren't just abstract curiosities. They're invitations to see the world differently, to appreciate the mystery woven into the fabric of existence. Science often promises answers, and quantum mechanics has delivered many. But it has also given us better questions. It has shown us that the deeper we look, the stranger things become, and that strangeness is not something to fear, but to embrace with curiosity and openness. As you drift towards sleep tonight, consider this. The atoms in your body, the ones that make up your bones and blood and breath, are humming with quantum uncertainty. Electrons exist in clouds of probability around nuclei. Particles tunnel through barriers. The very space around you vibrates with invisible quantum fluctuations. You are not separate from the quantum world. You are part of it. Every breath, every thought, every moment of existence is underwritten by these strange, beautiful rules. The universe is not a cold, mechanical place grinding away indifferently. It's a place of possibility and connection, where the future is not written, where observation and reality are intertwined, and where even the emptiest void is full of potential. Quantum physics doesn't just describe how particles behave. It reveals something profound about the nature of being. It tells us that uncertainty is fundamental, that connections transcend distance, and that reality is far richer and stranger than it appears on the surface. And perhaps that's the most comforting thought of all. In a universe governed by probability and shaped by interaction, nothing is truly fixed. Every moment holds infinite possibilities. Every measurement collapses a wave function, but somewhere in the vast landscape of quantum states, other possibilities still ripple through the fabric of reality. The universe is not predetermined. It's not finished. It's a work in progress, unfolding moment by moment, shaped by interactions and observations and the quiet, persistent hum of quantum fields. And you, resting here tonight, are part of that unfolding. Your presence matters. Your observations influence what becomes manifest. However subtly, the universe responds to your existence, not because you're special in a cosmic sense, but because interaction and observation are woven into the very structure of quantum reality. So rest easy. Let the strangeness wash over you like a gentle tide. Let the uncertainty be a source of comfort rather than anxiety. In a quantum universe, nothing is rigidly fixed. Everything is connected in ways we're still discovering, and even the smallest particle can profoundly affect the world simply by being observed, by being part of the great interconnected dance of existence. We've spent much time exploring the general strangeness of quantum mechanics, but there's a specific corner of the quantum world that deserves its own quiet attention. Deep inside the nucleus of every atom, inside the protons and neutrons themselves, a drama unfolds that's governed by one of nature's most powerful forces. It's called the strong force, and the quantum theory that describes it, quantum chromodynamics, reveals a universe even stranger than the one we've encountered so far. If you could zoom in, way down past atoms, past electrons orbiting nuclei, past even the protons and neutrons in the nucleus itself, you'd find something unexpected. Protons and neutrons aren't fundamental. They're made of even tinier particles called quarks, bound together by particles called gluons. Quarks are peculiar things. They come in 6 types, whimsically named up, down, charm, strange, top, and bottom. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. These quarks are held together by the strong force, and unlike any other force in nature, the strong force doesn't weaken as particles move apart. It actually gets stronger. Imagine trying to pull 2 quarks apart. In most forces, like gravity or electromagnetism, the farther you separate 2 objects, the weaker the force between them becomes. But with the strong force, it's as though the quarks are connected by an invisible rubber band. The farther you pull, the more the band stretches, and the stronger it pulls back. This creates a strange situation. You can never isolate a single quark. If you try to pull one away from its companions with enough energy, the rubber band doesn't break. Instead, the energy you've put in creates new quark-antiquark pairs from the vacuum, and you end up with new bound particles instead of a free quark. This phenomenon is called confinement, and it's one of the most distinctive features of the strong force. The theory that describes all this is quantum chromodynamics, or QCD for short. Its built-in analogy to quantum electrodynamics, the theory of how electrically charged particles interact by exchanging photons. But where electromagnetism involves electric charge, QCD involves something called color charge. Now, before you picture quarks as tiny colored objects, understand that color here has nothing to do with actual colors. It's just a label physicists chose to describe a property that comes in three types, whimsically called red, green, and blue. Every quark carries one of these three color charges, and every antiquark carries an anticolor. Just as photons carry the electromagnetic force between charged particles, gluons carry the strong force between color-charged quarks. But here's where things get interesting. Unlike photons, which are electrically neutral, gluons themselves carry color charge. A gluon might carry, for example, red and anti-green charges. This means gluons can interact not just with quarks, but with each other. This self-interaction of gluons is what makes the strong force behave so differently from electromagnetism. Photons don't interact with each other directly, which is why electromagnetic forces weaken predictably with distance, but gluons interact with themselves, creating a kind of self-reinforcing field that becomes stronger as quarks separate. Producing that rubber band effect, there are 8 types of gluons, each carrying different combinations of color and anticolor charges. They zip back and forth between quarks, constantly changing the quark's colors. A red quark might emit a red anti-green gluon and become a green quark. The gluon is then absorbed by a green quark, which becomes red. It's a constant dance of color exchange, happening at timescales so short they're almost incomprehensible. Inside a proton, which is about a femtometer across, that's a millionth of a billionth of a meter. 3 quarks are trapped in this gluon field, exchanging colors continuously. The quarks never escape. They're permanently confined, bound by a force that refuses to weaken. This confinement explains why we only ever see combinations of quarks that are color neutral. Protons and neutrons, for instance, contain 3 quarks of different colors, red, green, and blue, which combine to form a colorless state, similar to how red, green, and blue light combined to make white. Mesons, another type of particle, contain a quark and an antiquark whose colors cancel out. But individual quarks, with their unbalanced color charge, can never exist in isolation. The mathematics of QCD is notoriously difficult. Because gluons interact with themselves, the equations become enormously complicated, especially at low energies where the strong force is, well, strong. Physicists have developed sophisticated computational techniques, including simulations run on supercomputers to calculate predictions from QCD. And those predictions match experimental results with remarkable precision. One of the beautiful aspects of QCD is a phenomenon called asymptotic freedom. At very high energies, when quarks are extremely close together, the strong force actually becomes weak. This seems paradoxical, but it's a direct consequence of the gluon self-interactions. When quarks are nearly touching, they behave almost like free particles, barely interacting. But as you try to separate them, the force intensifies dramatically. This asymptotic freedom was discovered theoretically in the 1970s by David Gross, Frank Wilczek, and David Politzer, work for which they received the Nobel Prize in Physics in 2004. It explained a puzzling experimental result from the late 1960s when physicists fired high-energy electrons at protons and found that the electrons were scattering off point-like objects inside. as though the protons contained small, nearly free particles. Those particles were quarks, behaving freely at high energy thanks to asymptotic freedom. The strong force is responsible for holding atomic nuclei together. Without it, the protons in a nucleus would repel each other electrically and fly apart. The strong force, acting through the exchange of particles called pions between protons and neutrons, overwhelms the electromagnetic repulsion and binds the nucleus together. This force is what powers the sun and every other star. In nuclear fusion, hydrogen nuclei overcome their electrical repulsion, partly through quantum tunneling, as we discussed earlier, and get close enough for the strong force to bind them together. When they fuse, they release energy. That energy, generated by the strong force deep in the sun's core, eventually reaches Earth as sunlight, powering nearly all life on the planet. The strong force shaped the early universe in the first microseconds after the Big Bang. When temperatures were unimaginably high, quarks and gluons existed freely in a state called quark-gluon plasma. As the universe expanded and cooled, quarks became confined into protons and neutrons, and eventually those protons and neutrons combined to form the first atomic nuclei. Understanding QCD gives us insight into the structure of matter at its most fundamental level. It explains not just what protons and neutrons are made of, but why they have the properties they do, why they're stable, and how the strong force governs the behavior of matter under extreme conditions. And it reminds us, once again, that the deeper we look into the quantum world, the stranger and more intricate it becomes. Forces don't always weaken with distance. Particles can be permanently confined, and fundamental building blocks of matter are held together by self-interacting fields that create structures far more complex than the simple billiard ball picture of atoms that we started with centuries ago. The strong force, described by quantum chromodynamics, is a testament to the richness hidden in the fabric of reality, waiting patiently to be uncovered by curious minds willing to peer into the heart of matter itself. While quantum chromodynamics describes the strong force, another quantum field theory describes a force much more familiar: electromagnetism. It's called quantum electrodynamics, or QED, and it's arguably the most successful scientific theory ever developed. Its predictions have been tested to extraordinary precision, and it passes every test with flying colors. QED describes how electrically charged particles, like electrons and protons, interact by exchanging photons. It's the quantum mechanical version of Maxwell's classical electromagnetic theory, but it goes far beyond what Maxwell could have imagined. In classical electromagnetism, two charged particles repel or attract each other through an electromagnetic field that exists between them. The force is continuous and well-defined. But in QED, we think of the interaction differently. The force between two electrons, for instance, arises from them exchanging virtual photons. Imagine two people on ice skates throwing a ball back and forth. Each time one catches or throws the ball, they get pushed backward. The exchange of the ball creates an effective force between them. In QED, the ball is a virtual photon, and the force emerges from the exchange process. These interactions are visualized using Feynman diagrams, invented by physicist Richard Feynman in the 1940s. A Feynman diagram is a kind of shorthand, a simple picture that represents a complex quantum process. Lines represent particles moving through space-time. Where lines meet at a vertex, an interaction occurs. An electron emits or absorbs a photon, for instance. The beauty of Feynman diagrams is that they're not just pictures. Each diagram corresponds to a mathematical expression that can be calculated by adding up contributions from all possible diagrams for a given process. Physicists can predict the probability of that process occurring. And here's where QED shows its power. When you calculate these probabilities and compare them to experimental measurements, the agreement is astonishing. One of the most famous examples involves the magnetic moment of the electron, a property related to how the electron behaves in a magnetic field. Classical physics predicts a certain value for the electron's magnetic moment, but QED predicts small corrections due to quantum effects, virtual particles popping in and out of existence around the electron, subtly altering its properties. When these corrections are calculated to high precision and compared to experiments, the agreement extends to more than 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. This extraordinary agreement between theory and experiment makes QED one of the most precisely tested theories in all of science. It confirms not just that quantum field theory works, but that our understanding of virtual particles, vacuum fluctuations, and quantum corrections is fundamentally correct. QED also explains phenomena that classical electromagnetism cannot. It predicts the Lamb shift, a tiny difference in energy levels of the hydrogen atom that arises from the electron interacting with vacuum fluctuations. It explains the anomalous magnetic moment of the electron and muon. It describes pair production, where a high-energy photon can create an electron-positron pair from the vacuum, and annihilation, where an electron and positron can collide and disappear, converting their mass into pure energy in the form of photons. These aren't abstract curiosities. Positron emission tomography, or PTS scans, used in medical imaging, rely on electron-positron annihilation. When a positron from a radioactive tracer meets an electron in the body, they annihilate, producing two photons that travel in opposite directions. Detectors pick up these photons, and computers reconstruct an image of where the annihilations occurred, revealing metabolic activity inside the body. QED also underlies our understanding of light interacting with matter. Every time a photon is absorbed by an atom, causing an electron to jump to a higher energy level, or emitted when an electron drops to a lower level, QED describes the process. Lasers, LEDs, solar cells, photodetectors, all these technologies rest on principles governed by quantum electrodynamics. The development of QED was one of the great achievements of mid-20th century physics. Einman Julian Schwinger and Sin Hideo Tomonaga independently developed the theory in the late 1940s, for which they shared the Nobel Prize in Physics in 1965. Their work showed how to deal with infinities that appeared in early quantum field theory calculations, a process called renormalization that made the theory mathematically consistent and predictive. Feynman's approach, using his diagrams and path integral formulation, was particularly elegant and intuitive. It allowed physicists to visualize quantum processes and calculate probabilities in a systematic way. His diagrams have become iconic, appearing in physics textbooks and popular science books alike, a visual language for describing the quantum world. QED is a cornerstone of the Standard Model, the comprehensive theory of particle physics that describes all known particles and 3 of the 4 fundamental forces. While QED handles electromagnetism, quantum chromodynamics handles the strong force, and the electroweak theory unifies electromagnetism with the weak force, which governs radioactive decay. Together, these quantum field theories form a remarkably complete picture of the subatomic world. They explain how particles interact, how forces are transmitted, how matter and energy convert into one another, and how the universe behaves at its smallest scales. And they remind us that the quantum world, for all its strangeness, is also deeply logical and mathematical. The rules are precise, the predictions are testable, and when we check, nature confirms that we've understood something profound about the way reality works. As you rest tonight, consider that every interaction between charged particles, every electron flowing through a wire, every photon striking your retina, every chemical bond in your body, is governed by QED. The light you saw today, the warmth of the sun, the colors of a sunset, all emerge from quantum electrodynamic processes, from particles exchanging virtual photons in a dance choreographed by the mathematics of quantum field theory. It's a reminder that the universe, beneath its apparent complexity, operates according to principles we can understand, test, and verify. And that understanding, hard-won over decades of theoretical and experimental work, is one of humanity's great intellectual achievements. The quantum world has given us superposition, entanglement, and tunneling, but there are other strange effects lurking in the corners of quantum mechanics that deserve a moment of quiet contemplation. These phenomena stretch our intuitions even further, revealing just how delicate and peculiar quantum behavior can be. There's an old saying, "A watched pot never boils." It's meant to capture the feeling that time seems to slow when you're waiting for something, but in the quantum world, this saying takes on a literal physical meaning through something called the quantum Zeno effect. The quantum Zeno effect is named after the ancient Greek philosopher Zeno of Elea, who proposed various paradoxes about motion and change. In one paradox, Zeno argued that motion is impossible because before an object can reach its destination, it must first reach the halfway point, and before that, the quarter-way point, and so on infinitely. Of course, objects do move, but Zeno's paradox captures something about dividing continuous processes into infinitesimal steps. In quantum mechanics, the Zeno effect works like this. Imagine a quantum system that's evolving from one state to another. Left alone, it will smoothly transition according to Schrödinger's equation. But if you keep measuring the system repeatedly to check whether it has transitioned yet, something remarkable happens. The very act of repeated measurement can prevent the transition from occurring. This appears to contradict common sense. How can simply observing something prevent it from changing? But remember, in quantum mechanics, measurement isn't passive. It causes the wave function to collapse. Each time you measure the system and find it still in its initial state, the wave function collapses back to that initial state, resetting the clock on the transition process. It's as though you're constantly interrupting the system, never giving it enough time between measurements to evolve into the new state. The more frequently you measure, the more effectively you freeze the system in place. A watched quantum pot, quite literally, never boils. The quantum Zeno effect has been demonstrated experimentally with various quantum systems, including trapped ions and atoms. In one experiment, scientists prepared atoms in an excited state that would normally decay to a lower energy state by emitting a photon. By repeatedly measuring whether the atoms had decayed, they could significantly slow down or even completely inhibit the decay process. The atoms remained excited far longer than they should have, held in place by the relentless scrutiny of measurement. This effect has practical implications for quantum computing and quantum information. If you can use the Zeno effect to stabilize certain quantum states, you might be able to protect quantum information from unwanted changes or errors. Conversely, understanding how measurement affects quantum evolution is crucial for designing systems that need to maintain coherence despite interactions with their environment. There's also a flip side to the quantum Zeno effect called the quantum anti-Zeno effect, where frequent measurements can actually accelerate transitions rather than inhibit them. This occurs when the measurement process itself introduces energy or couples the system to its environment in ways that promote the transition. The balance between Zeno and anti-Zeno effects depends on the specifics of the system and how measurements are performed. The quantum Zeno effect is a beautiful example of how deeply observation is woven into quantum mechanics. It's not just that we learn about systems by measuring them. Measurement actively participates in shaping how systems evolve. The universe doesn't just exist independently, ticking along whether we look or not. At the quantum level, looking changes what happens. In 1924, Indian physicist Satyendranath Bose sent Albert Einstein a paper describing a new way to think about photons, particles of light. Einstein was impressed and extended Bose's ideas to atoms. Together, their work predicted something extraordinary. Under the right conditions, a collection of atoms could all collapse into the same quantum state, behaving not as individuals, but as a single, unified quantum entity. This state became known as a Bose-Einstein condensate, or BEC. For decades, this remained a theoretical curiosity. Creating a BEC required cooling atoms to temperatures just billionths of a degree above absolute zero, colder than anywhere in the natural universe. But in 1995, physicist Eric Cornell, Carl Wieman, and Wolfgang Ketterle succeeded in creating the first Bose-Einstein condensates in the laboratory, work for which they received the Nobel Prize in Physics in 2001. What makes a BEC so special? In normal matter, even when cooled to low temperatures, atoms retain individual identities. They occupy different positions, move with different velocities, and behave as distinct particles. But in a BEC, atoms lose their individuality. Their quantum wave functions overlap and merge, creating a single macroscopic quantum state that can extend over thousands or millions of atoms. Imagine a crowd of people standing in a room. Normally, each person occupies a distinct location. But in a BEC, it's as though all the people suddenly occupy the same space, moving in perfect synchrony, indistinguishable from one another. The entire condensate behaves like one giant atom, governed by a single wave function. This happens because of quantum statistics. Particles in quantum mechanics fall into two categories based on their spin: bosons and fermions. Bosons, which have integer spin, can occupy the same quantum state simultaneously. Fermions, which have half-integer spin, cannot. They obey the Pauli exclusion principle, which forbids two identical fermions from being in the same state. Photons are bosons, and so are certain atoms when their total spin adds up to an integer value. When cooled to extraordinarily low temperatures, these atoms' quantum wavelengths become comparable to the spacing between them. At that point, their wave functions overlap, and because they're bosons, they all condense into the lowest available energy state. The result is a form of matter unlike anything in everyday experience. Light passes through a BEC differently than through normal matter. The condensate can exhibit superfluidity, flowing without friction. It can support strange excitations like quantized vortices tiny whirlpools in the quantum fluid that only exist with specific discrete amounts of angular momentum. BCs have allowed physicists to observe quantum effects on macroscopic scales. Normally, quantum behavior is hidden in the microscopic world of atoms and particles. But in a BC, quantum phenomena become visible and measurable on scales you could almost see with the naked eye. If the condensates weren't so vanishingly cold and delicate, researchers have used BCs to test fundamental aspects of quantum mechanics, simulate other quantum systems, and explore exotic states of matter. They've created atom lasers, coherent beams of atoms analogous to laser light. They've studied how BECs behave in magnetic and optical traps, how they interact with light, and how they transition between different quantum phases. Superfluidium, liquid helium, discovered in the 1930s, involves helium atoms forming a quantum fluid that flows without viscosity. Superconductivity, where certain materials conduct electricity without resistance at low temperatures, involves pairs of electrons, called Cooper pairs, that behave like bosons and condense into a coherent state. BECs provide a cleaner, more controllable system for studying these quantum collective behaviors. The creation of Bose-Einstein condensates is a testament to human ingenuity and persistence. It took 7 decades to go from theoretical prediction to experimental realization, requiring advances in laser cooling, magnetic trapping, and evaporative cooling techniques. But the result opened a new window into the quantum world, allowing us to see matter behaving in ways that blur the line between the quantum and classical realms. Another strange quantum phenomenon emerges when electrons are confined to 2 dimensions and subjected to strong magnetic fields. This setup produces the quantum Hall effect, a discovery that revealed deep connections between quantum mechanics and topology, the branch of mathematics concerned with properties that remain unchanged under continuous deformations. In 1980, physicist Klaus von Klitzing discovered that when electrons move in a 2-dimensional layer at very low temperatures and high magnetic fields, the Hall resistance, a measure of how the material responds to perpendicular electric and magnetic fields, takes on precisely quantized values. Instead of varying smoothly, the resistance jumps in discrete steps, forming plateaus at values determined by fundamental constants. These plateaus are extraordinarily precise, so much so that they're now used to define the standard for electrical resistance. The quantization is robust, appearing in different materials and under varying conditions, always yielding the same values to extraordinary accuracy. The explanation involves quantum mechanics and the way electrons form discrete energy levels called Landau levels in a magnetic field. But there's more to the story. The quantum Hall effect is intimately connected to topology, to the global properties of the electron wave functions in the material. In 1982, physicists discovered the fractional quantum Hall effect, where the plateaus occur at fractional values of the original quantum Hall steps. This was even stranger and hinted at the formation of new types of quasiparticles, collective excitations of electrons that behave like particles with fraction electric charge. Robert Laughlin, Horst Sturmer, and Daniel Tsui received the Nobel Prize in Physics in 1998 for this discovery and its explanation. The quantum Hall effect and its fractional cousin opened up the field of topological quantum matter, where the focus shifts from local properties of materials to global topological features that are incredibly stable against perturbations. This robustness makes topological states attractive for potential applications in quantum computing, where maintaining quantum information against noise and errors is a central challenge. topological insulators, topological superconductors, and other exotic states of matter have since been discovered and studied, each revealing new facets of how quantum mechanics geometry and topology intertwine. These discoveries remind us that quantum mechanics continues to surprise us, offering new phenomena and new ways of thinking about matter, even decades after the theory's foundations were laid. We've touched on decoherence earlier, but it deserves deeper exploration because it helps answer one of quantum mechanics' most pressing questions. Why don't we see quantum superpositions in everyday life? Decoherence is the process by which quantum systems lose their quantum properties through interactions with their environment. When a quantum system becomes entangled with many environmental degrees of freedom, photons, air molecules, thermal vibrations, the delicate quantum superpositions that characterize the system become effectively inaccessible. The system appears to behave classically, even though the full quantum description still exists in principle. The timescales for decoherence vary enormously depending on the system and its environment. For a single isolated atom in a vacuum, quantum coherence can persist for seconds or even longer. For a large molecule at room temperature, coherence might last only femtosecond, millionths of a billionth of a second. For a macroscopic object like a cat, decoherence happens so rapidly that quantum superpositions are destroyed almost instantaneously. This explains why Schrödinger's cat thought experiment seems absurd. It's not that quantum mechanics doesn't apply to cats. It's that cats, being warm, massive, and constantly interacting with their environment, undergo decoherence so quickly that any quantum superposition of alive and dead states would collapse into a definite classical state essentially immediately. The cat is always either alive or dead because decoherence enforces this classical behavior long before any human observer opens the box. Decoherence has been studied extensively in recent decades, both theoretically and experimentally. Researchers have measured decoherence times for various systems, explored how different environments affect coherence, and developed techniques to protect quantum systems from decoherence. One approach is quantum error correction, where quantum information is encoded redundantly across multiple qubits in such a way that errors caused by decoherence can be detected and corrected without directly measuring the quantum state. Another approach is to isolate quantum systems as much as possible, cooling them to extremely low temperatures, shielding them from ultra-high vacuum. Despite these challenges, decoherence is also what allows quantum mechanics to reproduce classical physics in the appropriate limit. If quantum superpositions never decohered, the world would remain fundamentally quantum at all scales, and we'd never observe the definite classical outcomes we see in everyday life. Decoherence provides a natural mechanism for the emergence of classical behavior from quantum foundations. Understanding decoherence has philosophical implications too. It suggests that the collapse of the wave function isn't necessarily a mysterious instantaneous event triggered by conscious observation. Instead, it can be understood as a gradual process of entanglement with the environment, where quantum information spreads out into an ever larger system until it becomes practically irretrievable. This doesn't fully resolve the measurement problem. There are still debates about whether decoherence alone is sufficient, or whether additional interpretational elements are needed, but it shifts the focus from conscious observers to physical interactions with the environment, making the quantum classical transition seem less mysterious and more like an emergent phenomenon arising from quantum mechanics itself. Decoherence research continues to be active and important, especially as quantum technologies advance. Building practical quantum computers, quantum communication networks, and quantum sensors all require understanding and controlling decoherence. Every breakthrough in extending coherence times, every new technique for isolating quantum systems, brings these technologies closer to reality. And every experiment that measures decoherence teaches us something about the boundary between the quantum and classical worlds, about how the strange, probabilistic quantum realm gives rise to the familiar deterministic world we navigate every day. As you lie here, drifting towards sleep, your body is a battleground between quantum and classical. Quantum processes happen constantly in your cells. Electron transfers, proton tunneling, molecular vibrations, but decoherence ensures that these quantum events quickly become classical, producing definite outcomes that can be wired into biological function. Life exists at this interface, exploiting quantum effects where useful while remaining robust enough to function in a decohering, classical world. It's a delicate balance, and understanding it is one of the ongoing challenges of modern physics, straddling quantum mechanics, thermodynamics, and biology. The more we learn, the more we appreciate how subtle and sophisticated nature is at managing the quantum classical transition. We've journeyed far through the quantum landscape, from Planck's first tentative steps into quantization to the sophisticated theories and technologies of today. But for all we've learned, quantum mechanics still holds mysteries that remain unsolved, questions that keep physicists awake at night, and frontiers that beckon to future explorers. As we draw this journey to a close, let's peer into the unknown, into the questions that still haunt the quantum world. Despite a century of quantum mechanics, we still don't have a universally accepted answer to one of its most fundamental questions: what happens during a measurement? The equations of quantum mechanics describe how wave functions evolve smoothly and deterministically according to Schrödinger's equation. But when a measurement occurs, something different happens. The wave function appears to collapse suddenly and discontinuously into one of many possible outcomes. This collapse isn't described by Schrödinger's equation. It seems to be a separate, additional process. But what triggers it? What counts as a measurement? Does it require a conscious observer? Or does any interaction with a macroscopic apparatus suffice? Is collapse a real physical process, or just an update in our knowledge? Different interpretations give different answers, but none is universally accepted. The measurement problem isn't just philosophical hair-splitting. It has practical implications for quantum computing, quantum cryptography, and any technology that relies on maintaining quantum coherence. Understanding precisely when and how quantum systems transition from superposition to definite outcomes could help us build better quantum devices and might even reveal new physics. Some researchers are exploring objective collapse theories, which propose that wave function collapse is a real physical process triggered when systems reach a certain size or complexity independent of observation. These theories introduce small modifications to standard quantum mechanics that would be undetectable at the atomic scale, but would become significant for larger systems, naturally explaining why we don't see macroscopic superpositions. Other approaches focus on quantum gravity, suggesting that the collapse mechanism might be connected to gravitational effects that become relevant when different parts of a superposition correspond to different space-time geometries. Roger Penrose has proposed that gravity might induce wave function collapse, though this remains speculative and untested. Still others argue that decoherence, while it explains why superpositions become practically unobservable, doesn't fully resolve the measurement problem because it doesn't explain why we experience one particular outcome rather than another in any given measurement. The many worlds interpretation sidesteps this by saying all outcomes occur. But most physicists remain uncomfortable with the extravagant ontology that implies. The measurement problem remains one of the deepest puzzles in quantum mechanics, a reminder that even our most successful theories have conceptual foundations that we don't fully understand. Perhaps the greatest challenge facing theoretical physics today is reconciling quantum mechanics with general relativity, Einstein's theory of gravity. Quantum mechanics describes the behavior of particles and forces at the smallest scales. General relativity describes gravity and the structure of space-time at the largest scales. Both theories are extraordinarily successful in their domains, but they're fundamentally incompatible. General relativity treats space-time as a smooth, continuous fabric that can be curved by mass and energy. Quantum mechanics treats everything as fundamentally discrete and probabilistic. When physicists try to apply quantum mechanics to gravity, the mathematics breaks down, producing nonsensical infinities that can't be removed through the usual techniques. This incompatibility becomes critical in situations where both quantum effects and strong gravity are important, inside black holes at the moment of the Big Bang, and in any scenario involving extremely high energy densities or tiny distances. In these regimes, neither general relativity nor quantum mechanics alone can provide a complete description. The search for a theory of quantum gravity has occupied some of the brightest minds in physics for decades. Several approaches have been explored, each with its own insights and challenges. String theory proposes that fundamental particles aren't point-like but tiny vibrating strings. Different vibration modes correspond to different particles. String theory requires extraspatial dimensions beyond the familiar three, and it naturally includes gravity. In fact, gravity emerges automatically in string theory through a particular vibration mode of strings. This elegant feature has made string theory attractive, but it's proven incredibly difficult to test experimentally. The energy scales and length scales where string effects would become apparent are far beyond current experimental reach. Loop quantum gravity takes a different approach, attempting to quantize space-time itself. In this framework, space isn't continuous, but made of discrete, interconnected loops at the smallest scales, forming a kind of fabric or network. This discreteness provides a natural cutoff that prevents the infinities that plague other approaches to quantum gravity. Loop quantum gravity has made predictions about the structure of space at tiny scales and about modifications to black hole physics, but these too remain difficult to test. Other approaches include causal set theory, which treats space-time as fundamentally discrete and ordered by causal relationships, asymptotic safety, which proposes that gravity might be quantizable after all, if certain conditions are met at high energies, and various approaches based on emergent gravity, where gravity and possibly space-time itself arise from more fundamental quantum information theoretic structures. Some researchers have proposed that space-time might be holographic, meaning that all the information in a volume of space can be encoded on its boundary surface, similar to how a hologram encodes three-dimensional information on a two-dimensional surface. This idea, emerging from studies of black holes and string theory, suggests deep connections between quantum information, gravity, and the structure of space-time itself. The question of quantum gravity is intimately connected to understanding the nature of time, the origin of the universe, the fate of information that falls into black holes, and whether the Big Bang was truly a beginning or part of a larger, perhaps cyclical, cosmic history. Experimental tests of quantum gravity are extraordinarily challenging, but not impossible. Some approaches look for tiny deviations in the behavior of light traveling across cosmic distances, which might reveal the granular structure of space-time. Others search for signatures of quantum gravity in the cosmic microwave background, the afterglow of the Big Bang. Still, others hope to observe quantum effects in gravitational waves or in experiments that probe the interface between quantum mechanics and gravity using ultra-precise measurements. The resolution of quantum gravity, when it comes, will likely revolutionize our understanding of reality as profoundly as quantum mechanics and relativity did in the 20th century. It might reveal that space and time are emergent rather than fundamental, that information plays a more central role in physics than we currently appreciate, or that the universe is part of a larger multiverse with properties we're only beginning to glimpse. While foundational questions remain, quantum science is also advancing on practical fronts, developing technologies that will shape the 21st century and beyond. Quantum computing continues to progress. As of 2026, we're seeing steady improvements in qubit counts, coherence times, and error rates. Major technology companies, startups, and research institutions around the world are racing to build increasingly powerful quantum computers. The challenge isn't just building more qubits, but ensuring they can work together coherently and maintaining their quantum properties long enough to perform useful calculations. Quantum algorithms are being developed for specific problems where quantum computers might offer advantages, simulating quantum systems for drug discovery and material science optimization problems in logistics and finance, certain machine learning tasks, and cryptographic applications. While a fully universal, fault-tolerant quantum computer capable of tackling arbitrary problems remains years or decades away, specialized quantum processors are beginning to demonstrate quantum advantage for specific tasks, performing calculations that would be impractical on classical computers. Quantum communication is another active area. Quantum key distribution, which uses entangled photons to create secure encryption keys, is already commercially available. Several countries are building quantum communication networks, including satellite-based systems that can distribute entangled photons across continents. The vision is a future quantum internet where quantum information can be transmitted, stored, and processed across distributed networks, enabling applications we're only beginning to imagine. Quantum sensing exploits the extreme sensitivity of quantum systems to external influences. Quantum sensors are being developed to detect tiny magnetic fields, measure gravitational variations with unprecedented precision, create ultra-accurate atomic clocks, and image biological samples without damaging them. These technologies have applications ranging from medical diagnostics to navigation, from mineral exploration to fundamental physics experiments. In quantum materials, researchers are discovering and engineering substances with exotic quantum properties. Topological insulators, superconductors that work at higher temperatures, materials with unusual magnetic or optical properties. Understanding and controlling these quantum materials could lead to revolutionary technologies in energy, electronics, and computing. Quantum biology, while still controversial in some areas, is accumulating evidence that quantum effects play functional roles in photosynthesis, enzyme catalysis, bird navigation, and possibly other biological processes. If confirmed and understood, this could open new approaches to designing artificial photosynthetic systems, developing more efficient catalysts, and understanding the boundary between quantum and classical in warm, complex systems like living cells. Beyond technology and unsolved problems, quantum mechanics has left a profound philosophical legacy. It has forced us to rethink fundamental concepts, causality, determinism, locality, realism, and the nature of observation itself. Before quantum mechanics, most scientists assumed the universe was deterministic, that if you knew the complete state of a system at one moment, you could, in principle, predict its future with certainty. Quantum mechanics challenged this, introducing fundamental randomness into the fabric of nature. Whether this randomness is truly fundamental or emerges from something deeper remains an open question, but it has transformed our understanding of what it means for the universe to be lawful. Quantum mechanics challenged locality, the idea that objects are only influenced by their immediate surroundings. Entanglement shows that quantum correlations can span arbitrary distances instantaneously, though in a way that doesn't allow faster-than-light communication. This tension between quantum non-locality and relativistic causality remains one of the theory's most conceptually challenging features. It challenged realism, the idea that objects have definite properties independent of observation. In quantum mechanics, it's questionable whether particles have definite positions or momenta before they're measured. The properties seem to come into existence through the act of measurement, or at least become definite relative to a particular observer or measurement context. These challenges have philosophical implications. They inform debates in philosophy of science about the nature of scientific explanation, the role of observation in defining reality, and what it means for a theory to be true or real. They've influenced discussions in philosophy of mind about consciousness, free will, and the relationship between observers and the observed world. Quantum mechanics also exemplifies how scientific progress can proceed even when foundational understanding is incomplete. Despite ongoing debates about interpretation and measurement, quantum mechanics works spectacularly well for making predictions and guiding technology. This pragmatic success suggests that understanding and prediction can sometimes advance independently of deeper conceptual clarity, a lesson relevant to many areas of science. As we reach the end of this extended journey through quantum physics, it's worth reflecting on how far we've come. Not just in this video, but as a species trying to understand the universe. A little over a century ago, we had no inkling that energy came in quanta, that particles could behave like waves, that observation could influence reality, or that particles could be entangled across vast distances. The quantum world was completely hidden from us, waiting patiently beneath the surface of classical physics. Today, we have a sophisticated mathematical framework that describes quantum behavior with extraordinary precision. We've tested its predictions to more than 10 decimal places. We're building technologies based on quantum principles that would have seemed like magic to physicists of the early 20th century. We're peering into the heart of atoms, manipulating individual particles, and exploring how quantum mechanics shapes everything from the smallest particles to the largest structures in the cosmos. And yet, mysteries remain. Deep questions about the nature of measurement, the reconciliation of quantum mechanics with gravity, the interpretation of the wave function, and the ultimate structure of reality. These aren't failures, they're invitations. They're the questions that will guide the next generation of physicists, the mysteries that will yield new insights, new technologies, and perhaps entirely new ways of thinking about existence itself. Quantum mechanics teaches us humility. It shows us that the universe doesn't conform to our intuitions, that reality is stranger and more subtle than everyday experience suggests. It reminds us that certainty is rare, that some questions have multiple valid answers, and that the deeper we look, the more there is to discover. But it also teaches us wonder, the fact that particles can be waves, that the vacuum seethes with energy, that observation shapes reality, that connections transcend space. These aren't just abstract facts. They're invitations to see the world with fresh eyes, to appreciate the profound strangeness woven into the fabric of existence. You are made of quantum stuff. Every atom in your body, every interaction that keeps you alive, every thought passing through your mind rests on quantum mechanical foundations. You are not separate from this quantum strangeness. You are part of it, woven into its fabric, participating in its dance of possibilities and actualities. As you drift into sleep tonight, carried gently by these ideas, remember that the universe is vast, strange, beautiful, and still largely mysterious. Quantum mechanics has given us a window into that mystery, a way to peer behind the curtain of everyday experience and glimpse something deeper. The journey doesn't end here. For every question quantum mechanics has answered, it has raised new ones. For every mystery solved, new mysteries have appeared on the horizon. And that's exactly as it should be. Science isn't about reaching final answers. It's about asking better questions, exploring further, and never losing the sense of wonder that draws us to look up at the stars and down into the atom and ask, what is this? How does it work? What does it mean? Thank you for staying with me through this long, gentle exploration of quantum physics. If you found this journey meaningful, a like and subscribe really helps this channel continue creating these soft explorations of science. And to all of you already here, your presence makes this work worthwhile. May your dreams be filled with possibilities. May your mind rest in the comfortable uncertainty of the quantum realm, and may you wake tomorrow with a renewed appreciation for the profound strangeness and beauty of the reality we inhabit. Sleep well. The quantum universe will still be here in the morning, waiting with more mysteries to explore, more wonders to discover, and more invitations to understand the extraordinary nature of existence itself. Good night,